Welcome, everyone. We'll start about 1 minute after the hour. If you're just coming on now, we'll start in just about a minute. Okay, well, I'm sure that people are still getting on, but why don't we go ahead and get started? Welcome to the Air-Sea Fluxes from Space webinar series. Today, we're fortunate to have Hiroyuki Tomita from Hokkaido University, who is the PI of the J-OFURO project. Tomita-san is going to talk about J-OFURO3 Air-Sea Flux product, the current status, and the future. So take it away.
Thank you very much. Can you hear me?
Yes.
Okay. Thank you very much. This is Hiroyuki Tomita from the Hokkaido University in Japan. So today I'd like to talk about my project, J-OFURO, which is an SC Flux product from the space. So the first, I'd like to give you very simple, quick background of about the surface flux. As you know, the surface flux connect the ocean and the atmosphere. I think that it's like a communication language between the ocean and the atmosphere. So the accurate estimation of the flux is indispensable for better understanding of the air-sea interaction. However, the in-situ observation does not cover the global oceans and the severe conditions. So that's why we need a satellite-based estimation from the space. Okay, the J-OFURO is a research project to do this. So officially, the J-OFURO stands for the Japanese Ocean Flux Dataset with use of remote sensing observations. A little bit long, but it's called as the project, the J-OFURO. And J-OFURO utilizes the multi-microwave satellite, like JAXA's AMSR2, SSMI, and SSMIS for the estimation of the surface heat, momentum, and freshwater fluxes. In this research project, we are doing the research on the development of the estimation method and understanding the air-sea interaction and publication of the data product. So yeah, there are some similar projects like Iframel in France and HORPS in Germany, and the C-Flux and the OFLux in the US project. The OFLux is a very famous, and the last week, Dr. Lee San-Yu introduced this project. So the J-OFURO has a bit long history from 2000, about 2000. So for now, the third generation of the dataset, J-OFURO3, is an open dataset in the project, from the project. So yeah, the J-OFURO3 provide the open access data and open data via the data integration analysis system in Japan, DS. And here is the specification of the J-OFURO product. And yeah, now we are providing the third generation data set. And we did some minor update in the previous. But for now, the version 1.2 covers about 35 years from the 1988 to 2022. And the temporal average on the spatial grid size is daily and about 0.25 degree grid. And the flux, turbulent heat flux was calculated by the bulk formula proposed by the Core 3.0 algorithm from these state variables. The state variables, one of the state variables, the SST, and also the humidity near surface, and wind speed and air temperature. The most important feature of in the J-OFURO3 is using the multi-satellite product or multi-satellite sensors like this. For example, for SST, we obtained a daily SST product from by the ensemble median of the multiple global products. And for the humidity and for the wind speed, we obtained data from the multi-microwave radiometers and or scatterometers like this. But for the air temperature, satellite cannot retrieve the temperature. So for now that we are using the NSF, the atmospheric reanalysis air temperature data. So yeah, I said the one of the future of the multi-satellite it's one of the future of the J-OFURO3 is a multi-satellite observations. This is an example of the scalar wind speed observation in a day in the various satellite sensors. So if we use all of the data, we can get better coverage for the global ocean and better accuracy. We can get a better accuracy. So this slide shows the impact of the multi-satellite observation. So on the accuracy, the left panel shows the impact on the accuracy. Accuracy means root mean square the error compared with the buoy observation, in situ buoy observation. So the left figure shows and in the left figure, the horizontal axis indicate the number of the satellite sensors, and the vertical axis shows the root mean squared error of the latent heat flux. So I will skip the detail of the comparison with the in situ observation, but this figure clearly shows the impact of the multi-satellite observation like this. And the right panel shows the another aspect of the multi-satellite observation. And top in the top, there are two figures showing the high-pass SST and surface wind speed spatial pattern in the North Pacific crucial region and in the North Atlantic, the Gulf Stream region. So yeah, you can see the very clear positive relationship between the high pass, I mean the small scale SST and wind speed like this. So this relationship is very important to understand the mid-latitude LCE interaction. For example, the correlation indicate that the positive impact on the atmosphere of the ocean. So this correlation was observed well in the J-OFURO3 product. And this is also the multiple satellite impact on the correlation between the SST and the wind speed. You can see if we use the number, if we use the large number of the satellite observation, you can see the clear relationship between the SST and the wind speed like this. That's importance of the use of the multi-satellite observation. Okay, from here, I'm like to talk about humidity. Yeah, the humidity in the especially near surface air specific humidity, QA over the global ocean is very, very important because QA is an essential climate variable and is also one of the surface flux state variables. So however, there is a large uncertainty in the estimation of the QA, and it's a major error source in the flux estimate. So the satellite microwave radiometers like SSMI and AMSA3 are major important instrument to estimate the near surface specific humidity. So there are several algorithms to obtain the QA from the microwave radiometers from the 1986 to the recent years. So one of the algorithms, Tomita, throughout 2018, which was developed by me. We call it the T18, was used in the J-OFURO3 calculation. So one of the feature of the T18 these algorithms can used for the multi microwave radiometers. Most of the previous algorithm was developed only SSMI or SSMIS, but the T18 is used for the multi microwave radiometers. So the algorithm is based on the semi-linear relationship between the brightness temperature TB observed by microwave radiometers and in situ QA observations. So yeah, the left panel shows the amplitude microwave radiometers. the observation frequency and the sensitivity to the physical variables. So the most important part in this figure is the absorption by the water vapor around the 22 gigahertz. So the amplitude observed the 24 gigahertz. This observation this observation will correlate with the in situ observation of the QA like this. This is a scatter diagram between the observed QA and the brightness temperature of the 24 gigahertz. You can see the semi-linear relationship between them. But still have the large scattering and it looks non-linear relationship. So the scattering or non-linearity is from the vertical moisture profile. So in this study, we calculated the water vapor scale height, HV, described the Kanemaru and Masunaga, and we calculated HV from the satellite observation and atmospheric reanalysis data as shown here. So this slide indicating the characteristics of the water vapor scale height, HV. So the horizontal axis is showing the water vapor scale height, HV, and the vertical axis showing the pressure level in the atmosphere. So that you can see the very clear relationship between the HV and the humidity profiles. I say that the color is normalized humidity in the atmosphere. So anyway, we can say that HV represents the rough shape of the vertical profile of the water vapor. So we try to combine this kind of information and to the retrieval algorithm using the microwave radiometers. So this slide shows the relationship with, among the TB, QA, and HV. The x-axis, horizontal axis of each figure, showing the SSMI, one of the microwave radiometer, brightness temperature at 22 gigahertz, and the vertical axis shows the in situ QA, surface humidity. So again, you can see the semi-linear relationship between them, but there's some scattering. But if the other color means the HV calculated from the satellite and the atmospheric reanalysis data. So you can see the HV can divide the scattering. If we use the HV information, we can get better relationship between the brightness temperature and near surface humidity like this. So yeah, finally we combined this kind of the relationship on the TB and QA and HV to the algorithm, retrieval algorithm. So we did a validation with the independent in situ observations. So these figures are showing the scatter diagram between the buoy observation and the satellite based estimation. The color is the normalized data density. So most of data is located in the tropical Pacific region, but we can see the other we can see the other data in the mid-latitude, high-latitude region. So anyway, these figures showing that our algorithm, I mean T18, looks nice result compared with other satellite retrieval algorithms. Okay, but I think that this is I think that T18 looks better than the other product, but some say that the T18 using the atmospheric reanalysis information. So that's a kind of problem for pure estimation of this surface humidity from this only satellite observation. So now we are trying to the new algorithm without atmospheric reanalysis information. So we are doing the something using the neural network algorithm. I skipped the detail this algorithm because that is not published, but you can say the new algorithms are becoming better at running the vertical water vapor scale height HV without atmospheric reanalysis data. So you can see this is the different comparison between the RMS error among the research algorithm. This is a T18 score, about 1.2 gram per kilogram. But yeah, our new algorithm looks similar score with the T18 without no information from the atmospheric reanalysis data. Okay, that's new aspect of the development of the algorithm. So more recently, we are trying to develop the humidity algorithm for the tropical cyclone region. It's I know it's a very challenging task. So yeah, but I'm trying to get something. So this is an example of the results. This is a special pattern of the QL over amplitude ascending pulse in the tropical cyclone in Chami in 2018. So right panel shows that standard of the J-OFURO3 global algorithm. So, and the left panel is a new algorithm for TC. So you can see the basic algorithm cannot observe the humidity in near center of the tropical cyclone like this, but the new algorithm can observe the QA, even in the near the TC. Of course, the near center is very in near center. We did not this well, but the comparing the previous one, we can get some nice estimation. So in the Nagoya University, Nagoya University people did the in-situ observation by the atmospheric drop zone, like a radio zone. So we can compare our new estimation and in-situ observation, in-situ drop zone observations. The red line is a drop zone, and blue dot are showing our new estimate. Yeah, there's some bias problem, but it looks nice compared with the previous one. So the key of the algorithm is using the AMS2 low frequency channel. So this figure showing the scatter diagram between the T-parak drop zone QA and AMS2 QA. So we tested the 4 different algorithms that use a different observation channel, especially the algorithm 2 and 3 are using the low frequency channel, like a 10 gigahertz. You can see the 10 gigahertz observation is important to estimate the QA in your TC center like this. But there's some problem, bias problem, but it's under development something. So this is a different example of the new algorithm for TC, and the top panel shows the comparison of the standard J-OFURO3 product and very high resolution coupled simulation done by the WADA et al. And also we compared several atmospheric renaissance products and satellite product. This is our new estimate for TC. Yeah, it looks a little bit noisy, and it looks very high humidity near the center. But if we compare the high resolution simulation, it looks realistic of the pattern, the humidity in their GC centers. Okay, okay, let's move on the different talk about long-term variation. It's a I'm sorry, it's quite different topic, but it's important for climate study. So this is showing the long-term variation, the global mean of the evaporation, latent heat flux, like evaporation. And you can see recently we can see the positive trend in the evaporation, in the middle of the period. But there are significant discrepancy among the product like this. So one of the reasons of these discrepancies is from the humidity estimate. So, but we didn't have the in situ observation to check the long-term variation. But recently, we can use the new in situ observation data set developed by the UK Met Office. It's the Hokudai SDH marine product developed by the UK Met Office related as well to 2020. So we recently we are trying to compare our product with this long-term climate monitoring data set. So yeah, this is the comparison result for the global mean of the humidity anomaly from the 1988 to 2022. And blue line, the Hokudai SDH in situ observation, and red line is the J-OFURO version 1, J-OFURO3 version 1.2. So you can see the very nice agreement with the long-term variation of the humidity like this. But one important thing is intercalibration of the sensors. So if we see the data without intercalibration, it looks very strange and artificial trend are found like this. So an important point of using the multi-satellite observation. Okay, lastly, I'm talking about our future plan of the J-OFURO. Actually, we said that there are 20 years history of the J-OFURO development. But the first version was released in 2002. After 8 years, we released the J-OFURO3, and after 9 years, we released our J-OFURO3. So I'm thinking of the J-OFURO4 the next generation of the product. So one of the key point is the new sensor, new microwave radiometer. I think the JAXA, Japanese agency of the space agency, now we are planning the next generation of the amateur series, like amateur as the amateur 3. So I hope that amateur 3 is very close. But the JAXA is planning the launch. JAXA planned the launching the amateur 3 in this year. I hope everything. I hope the success of the launching. But the amateur 3 has a new channel with 183 gigahertz, which is another major absorption by the water vapor, so that it will help the estimation of the surface humidity, which is very important for estimating of the acid flux. So, okay, last slide. I will summarize part of the J-OFURO, the current status, summarized from here. Currently, the J-OFURO3 version 1.2 data are available on the DS repository in Japan. But you can use the our data as public open access data. There are several papers with the open access like this. So recently, we are trying to develop the new line of the product for the tropical cyclone named J3TC. That's a Flux product for tropical cyclone study, but it's still under development. So in the future work, I'm thinking of the J-OFURO3. So the key point is the development the new algorithm for the QA using the GMI and AMSA3 new sensors. Okay, that's it. Thank you very much.
Thank you so much. Wonderful talk. Questions? And maybe while people are thinking of questions, I'll ask about resolution. So you're doing this in J-OFURO3 at daily and quarter degree. What do you think are the possibilities for doing things, or the need even for doing things at sub-daily or smaller than quarter degree?
Yeah.
What would it take to get there?
Yeah, but one of the things for the temporal resolution, we need high frequency observation. So if we have many satellite observation, we can get better temporal resolution. I think one of the things is using the small satellite observation. And another part is spatial resolution. It's a very hard task, hard issue. But AMSA3 new sensors in the JAXA slightly better spatial resolution like this. They are planning to making the higher resolution version of the SSD product. But I think that it's a slight improvement, but it's one of the things.
Thanks. I see that Megan has her hand up, Megan Cronin.
Hi, Tomita-san. Great talk. I have the same question as Deidre has on the chat, which is, what would it take to make this, more timely, like more near real time? I've worked with this product and I am so impressed by it. It compares really well against all of the mooring observations that I have used. I've tested with it in the tropics and Kyo and Papa. It is a great product. But my complaint is that it doesn't go up to the present. So what would it take? And it looks like with all of these multi-satellites that, there's a lot of dependencies upon other groups and other satellite groups. But is there, could the satellite community help with creating well, just go ahead and answer it. What does it take to make this real time?
Yeah. It's hard to answer the question. That's an important point. Real-time distribution of the data. So
Can I ask a clarifying question, Megan?
Yeah.
Do you want near real time, so sort of 6-hour delay or less, or do you just want it up
Timely.
to 2 weeks ago or a month ago?
2 weeks ago would be fine. 2 weeks ago would be fine. It's just right now it's 22, which is, better than the last time I looked at this. But yeah, it'd be great if it was even a month ago.
Yeah, it's one of the bottleneck of the is intercalibration. Like this. We need careful check the difference between the sensor to sensor. So we need much time to see the difference between among the sensors. So that's one of the reason we can now we don't have the real time product.
But aren't there other groups that do the merging that you could rely upon so that it's not you? I mean, my understanding is that you have a very small shop. It's just pretty much you here. So, I mean, can you rely upon other groups to do this intercalibration and the merging and the, getting this to be, get all the inputs for you?
Yeah.
And maybe this is a question for others on the call.
Maybe the related question is, how much does it degrade the product if you take what's available with only a day's delay and without having the time to do a full intercalibration?
Yeah. Okay, I will think right there about this issue.
Okay.
It's okay.
All right. Thank you.
Now, Deirdre Byrne
Thank you very
wrote
much.
daily.
Yeah, now
Is
providing
that
daily.
meaning, Deirdre, that you would like products with a day delay or
Daily.
less?
Oh,
Okay.
yeah.
So Megan's willing to take a couple
Yeah.
weeks of latency for science, but Deirdre wants something more operational. There are a lot of users.
Hurricanes.
There's another question in the chat from Qidong Zhang. Do you want to ask your question directly, Qidong?
Sure. Simple question. How is your product compared with
You're getting lots of noise and not hearing you.
I'm sorry. Then probably you can read the question.
Okay, I'll read the question, which is, how is your product compared to OA Flux of Lisan Yu? And I think Lizanne is on the call, so there's room for full discussion on this.
So Lisa asked me something. I didn't
Qidong
hear.
asks how your product compares with OA Flux.
I can see the question. Yeah, the comparison with the OA Flux. Actually, I did inter comparison with the OA Flux, maybe the 1 degree grade product. So, for example, this figure is showing the comparison with the OA Flux with green colors. So, yeah, I don't have much information about the difference between the OA Flux and the other product, but yeah, we are doing we need a inter comparison among the product. So I'm thinking that recent OA Flux 2 is a the latest version of the OA Flux. So that if I have the chance and data, and we can compare the J-OFURO3 with the OA Flux 2. That's okay, listen.
Lizanne, do you want to go ahead?
Hi. Thanks for the great.
Oh,
Oh, you've muted yourself.
Sorry.
There we go.
Thanks for the great talk. I'd be happy to compare with your products with the OA Flux 2. I don't know about how these figures made. I was like a little bit surprised, but it seems like different from my version. Maybe it's the old version, but anyway, that's the OA Flux 1, and we are phasing it out. I'm wondering, I mean, your talk emphasized a lot about humidity retrieval, and it seems like your temperature is just taken from the NWP models. So I'm wondering, do you have any plan to upgrade your temperature rather than just taking from NWP? And how is the comparison between your temperature versus buoy? Because right now your humidity seems like comparable, but your temperature, I'm not so sure. You have not seen any, have not shown any comparison.
yeah. As you said, our product is our product J-OFURO3 using just sorry.
Right.
Using the NWP model and the analysis. So that obviously the problem is in the air temperature. We did a comparison with the in situ observation. We can see the very severe positive temperature bias in the NWP model. So that is the reason of the error, the bias error in the total. surface heat flux unit. The major source of the error is air temperature. So it's the largest problem in the J-OFURO3.
Do you have plan to improve this air temperature estimate?
Yeah, one of my students developed the correction method of the NWP TA air temperature. He developed the correction method of the air temperature. So that's one of the I don't know. It's one of the way to improve the total flux estimation, I think.
Thank you.
Other questions? Can I ask, looking toward the future, I think the European Space Agency is planning to launch SIMR, sort of outside the window of you even doing your next generation J-OFURO3 product. But I guess that's a very large antenna microwave system. Have you thought about what that might do for this product?
SIMR in the
Yeah.
that SIMR, maybe SIMR had the 24, 22
29 or
gigahertz.
30 or 31.
Okay. So
Somebody on the call might know.
I don't know the detail of that SIMR, but SIMR has you said SIMR has a very large antenna. So that's very interesting. So yeah, we are trying to use the SIMR observation for the future development of J. So I will check the information of the SIMR.
And then can I ask also, what do you think the gaps are in the satellite observing system? If you could design a satellite to best meet the needs of J-OFURO future products, what traits would it need to have?
I'm sorry, I didn't.
If you could design a satellite, what would it do? What are the gaps?
Oh, that's an interesting question. Yeah, I think we need more channels because the more channel allow us the much information from the atmosphere and the near surface. So that's like for example, like a hyperspectral microwave radiometer is my dream. That's a very tough technology, but it's hyperspectral microwave will help ours.
That sounds great. I have to figure out how to propose it. Any other questions? If not, thank you so much for a really good talk and great discussion. This was a lot of fun.
Thank you very much.